Okay, we talked about Mosey, Dragon, and Firefly at least, so different types of cache coherency. One thing we kind of breezed over is how exactly these are implemented. You know, what is it we do exactly in order to keep everyone up to date. Over here in our standard bus architecture, this is usually pretty simple. You just have extra lines on your bus that are doing the snooping. The problem is, what if you have this architecture and then they're connected via some interconnect to another processor somewhere else? How do you maintain cache coherency across all that? The other issue is that with the snooping cache, even if you had a single bus, if you had 1,000 cores, that's going to take quite a while for the whole bus to interact with each other. So there might be some scalability issues, is what we're talking about here. When it comes to latency, which parallelism's fundamental advantage of snooping because it's a broadcast, so it talks to everyone at once. Let's see, cache coherence, physical bus, but still snoop. Yeah, the problem is once you get outside of this bus architecture, as I was talking about, things start to get a little tricky about how you're going to forward all the snoop messages around. One way we get around this is we use a directory at memory which says which processor is the writer, which processors are the shared readers. Remember, think about it, we're over here. I'm using P over here, but those are really just cores. And this might be P0. You might have P1 over here connected via Ethernet. I don't know why it has 3 or 4, but Ethernet to the other P1, and of course P2 might be over here, so forth and so on. So how would you keep all this shared? Well, you might have a directory, maybe this guy's memory, or you might actually have another piece of memory, which is more what happens, next to your Ethernet, which keeps track of who is the writer and who is the reader. So the problem here is now a dirty miss requires 3 hops, because in the regular Snoop, you just have the requester and then he goes to owner, but now you have to go to request, you have to go off your chip to the directory, find out who the owner is, and then get that and move over. So you have to go to directory, then to the owner. Because remember, this is Ethernet connects here, you might have a switching network, and then that one goes to P1, this one goes to P1. So you'd have to go to the directory, come back, then to the processor. So you've added another hop.
So a lot of time.
Yeah, a lot of time with these directories. But what else are you going to do? Teleport. They can just make mini DeLoreans. We'd be good to go. All right. Directory implementation. Well, where do we implement it? You could put it into main memory, record state line. Other CPU's commands are not snooped. Instead, the directory forwards the relevant commands. Powerful filtering. Let's see. Meanwhile, bandwidth. Powerful filtering effect. Only observe commands that you need to observe. Sure. Bandwidth at directory scales by adding memory controllers as you increase the size. So that's good because you'd have, remember, you have Ethernet here and you'd have little memory controllers down here, or you'd have your directory up here as well. And then each processor would keep a directory with the other little memory controllers. Squeaky. Okay. So the nice idea, centralize the directory. Hold on a second. We didn't talk about shortcomings. Indirection through a directory has latency penalty. That's what I was talking about here. Now you have more hops because you're going through a directory now. I'd say if shared line is dirty, the other CPU's cache directory must forward. So if you have the implementation where each processor has its memory in each directory, now when you have to do an invalidate or a shared line, all the directories have to be updated as well.
Latency, latency, latency.
Yep. Sadness, sadness, sadness. Another one to do is what I was talking about. You just have one centralized directory, which is nice because you can somewhat help with the traffic, but then you have to kind of go off Ethernet in order to do anything. Okay. All right, hold on. Just give a moment here. Yeah, so, okay. Notice that this architecture has changed a little bit. Now you have memory modules for each processor, so to speak, that have their own direct, well actually, they're not for each processor. You have multiple memory modules. Okay, hold on. Beforehand I was saying you have one massive directory. Now what we're saying is that you split up your main memory into having modules and then a directory for each one. Then the directory can be distributed, which means that instead of having one giant brain, you at least can have multiple little ones, and that way your interconnect network knows which directory to go to, which does help with your scalability. You understand the advantage of this, at least somewhat?
Is it less hops?
It's not. It is fewer hops, because if you know the piece of memory is right here, then and you have let's see, shared, and this guy needs to go to modified. He knows, oh wait, he's shared. You still have to go to main memory to know it, invalidate him, and then he gets the main memory, or then he gets modified. Sorry. The advantage is that you only interact with this as opposed to these two guys. And since you have it as a module, you can just plug and play new module chips at the time. It also allows your interconnect network to be point-to-point as opposed to a bus. So while this is happening, this guy can go and talk to the other modules.
And they're divided by memory
Yeah.
addresses?
Yeah, exactly. How big are these? Whatever they determine to be the right size.
High speed?
Sure, high speed, you know, I don't know, 8 meg modules, sure, whatever. We already went over this. Oh, we just did this. Oh, look at it again. Local cache suffers a miss. Line in remote cache is in M state. It is now the owner. It cache reads from the local controller to home memory controller up here. Memory reads the cache, so it updates its memory controller as well. Owner data back to memory changed to S. So he goes to S and he should go to O is what this should happen. You are interacting with the controller, but luckily these two things can happen somewhat in parallel because your interconnect does not have to be a bus anymore. And this does not matter. Okay. How can you eliminate one hop? So normally, I think this is probably the best picture we have yet. Read from the memory controller. This guy owns it, goes back to memory, and then he reads the memory.
Boo.
Boo. What could happen? Reads, cache says, hey, the read needs to go here. Send it directly while acknowledging the memory controller. The idea is that these two guys can happen in parallel. So now you're down to 3 hops as opposed to 4. It's still more hops than normal because usually you'd only have 2. Local controller would say, hey, read. This guy would say, here's your data, and it would only be 2 in a regular Snoopy cache. But if you do need a directory controller, and you're adding 1 more hop as opposed to doubling it. Okay, as you can see, late 90s and early 2000s, ISCA is where a lot of this research was done. It's as you probably guessed, it is somewhat expensive, performance-wise, to do. So we usually just try and keep with simple snooping caches. But hopefully, if you're doing high performance, I mean, you got to do something like this. But most of the time, you'll probably just see regular snooping caches and not this going around unless it's needed. And I think we don't need this. Okay, good. You don't need this for your assignment. All right, any questions?
Yeah. No, that's. So on the project, when you're like, if you find any useful information, send it to me. Do we get bonus points for that?
Yes.
Oh, really?
Yes.
Oh. Cool.
Everyone got that?
What project is
The midterm.
Midterm.
it? Okay.
Have you started the midterm?
So if we find useful information, bonus
I just have
points.
to compile. Thanks, Bart.
What's that, Bart?
I said we get bonus points for useful information.
Now, did you get the full system compiled or just the syscall emulation?
I got what you said to do on the GitHub.
Oh boy. Okay. We'll see what happens. This will be fun.
Well, I'll just get you a treasure trove of information and just get a ton of bonus points.
I didn't do my project, but I got all this information.
And the examples work.
Oh, good. Yeah, give me working examples. That'd be nice.
So are you done for the day?
Yes. Anything
Really?
else, guys?
Well,
Oh,
what
you
about
were,
the final?
yeah, what about the final project that you promised to assign today?
I
hate
did?
for you to go back on that agreement. Yeah,
Oh, I totally dropped the ball on that.
you did.
I did.
Because we were supposed to get it the end of this month so that we could start it before, because it was going to be assigned before the other one was due.
When's the other one due? Isn't it next week?
April 3rd, yeah.
No, Tuesday.
Yeah.
Unless you want to push that back.
No,
Nah.
it's not happening. Okay. Well, your final project, if you need to think about it, is just going to be modifying the Gem 5 simulator to add something like cache coherency or whatnot.
What you mean?
Well, it's a simulator, right?
Yeah.
So it has code.
No. As in the source code for it.
Right. We have to do a research project. That's a requirement.
We're researching how to get Gem 5 to run, period. It's very arduous.
Does it involve programming, the last one?
Say that again?
Does the final involve programming?
Yeah, they all do. Except for your book assignments. It's been a while, Jordan?
It has.
Yeah, this is probably the worst. Wait, is this your first semester as grad student or?
That was my last semester.
No.
I'm done May 5th.
Assuming your class doesn't screw us all over.
Yeah. It's past 16, so it's like the point of no return.
Matt, you know all my courses have a lot of programming in them.
Always.
Except operating systems, that's true.
Matt just warned me.
So,
On a scale of 1 to 10, compared to the out of order simulator, how feasible do you think it is to get the Gem 5 stuff by April 3rd?
8.473.
That's on a scale of 1 to out of order being the badness.
Wait, hold on. Which one's which? So one means it's not going to happen, and 10 means it will.
No, 1 means it wouldn't be too much of a hassle. 10
Oh,
means
so
out of
3.48.
order. Oh, cool. Cool. I guess I'll have to return that Badger and the 16 pack of energy drinks.
How many badgers do you have?
None. I get a honey badger though, they're so cute.
All I can remember is that. Wait, are we still?